Hello and welcome back to CS300 Introduction to Algorithms. And we are talking about the virtues of computer science and the examples for them. To recall, first virtue is full problem specification. Second virtue is algorithm design and their analysis regarding correctness and computational cost using fourth virtue, fully specified primitives, and finally computational complexity to prove algorithms optimal. And if they are, then we have succeeded, we're done. We have found the asymptotically optimal algorithm, and then we can start and should start optimizing according to Donald Knuth, because premature optimization is the root of all evil. What does it mean? Premature optimization, it means when we have not yet found the asymptotically optimal algorithm. In this case, we should start over from square one, actually square two in all this stuff virtues, namely start over devising a better algorithm, analyzing again and trying to prove that optimal or not. And to illustrate that, we have already considered a very simple example, namely the example of powering problem, where we are only allowed to use multiplication as primitive. No other primitives are allowed, and where every multiplication is supposed to cost one chart. That's part of the algorithm design, right? Operations which are allowed and how much they cost. And also the number n is supposed to be fixed here to the exponent to which we are asked to raise the given argument x. X is an input and n is arbitrary but fixed. And the first algorithm we have devised is simply repeatedly multiplying x to itself n minus 1 times. That means this algorithm in this superficial and arbitrary example incurs a cost which is linear O of n, because the n minus 1 can be ignored asymptotically. And we've asked whether this is optimal, and it turned out it is not optimal. Linear is not optimal. It can be beaten. How can it be beaten? With a more efficient algorithm, an algorithm which is called repeated squaring. And we've introduced and analyzed this algorithm in its recursive variant, namely, suppose that n is even, then we can compute x to the n by first raising x to the n over 2 by induction hypothesis or recursive call, since n over 2 is an integer if n is even. And then taking the result of that recursive call, which I leave to you to unroll and spell out as an explicit algorithm with or without pseudocode, then multiply that result to itself, thus squaring it. And observing that squaring just means multiply the previous intermediate result with itself using one multiplication. Squaring by itself is not among the permitted operations, but can be kind of expressed as multiplying some previous intermediate result with itself. And in case that n is odd, a little bit more effort is needed. Namely, in this case, n minus 1 over 2 is a natural number. N minus 1 is then even, divided by 2 is a there's no fraction. And thus here the recursive call or hypothesis, this can be computed using a certain number of operations, which we'll analyze in just a minute. then square that intermediate result to get x to the n minus 1, right? And then perform another multiplication with x to finally get x to the n. So that here, these mathematical equalities are kind of obvious, right? And they lead to an algorithm for each n, which I refrain from spelling out in full pseudocode. Instead, so the correctness of that algorithm is obvious, or this may be less obvious at first sight, is the cost incurred by these algorithms, namely the number of multiplications. And for this end, we have devised such a recurrence where t of n denotes the number of multiplications incurred in case of the exponent n. And if exponent n is 1, then there's nothing to do, no multiplication, 0. Whereas in the general case, either there's this recursive multiplication, which is n over 2 rounded down. Maybe in the even case, it's just n over 2. In the odd case, it's n minus 1 over 2, which is the same as n over 2 rounded down, plus either one multiplication for the squaring part, or plus 2 multiplications squaring and another multiplication, as you can see here. So this is now a recurrence in the sense of discrete mathematics for the number of multiplications incurred for the cost of our algorithm, which is called repeated squaring because it performs mostly the squaring and sometimes the multiplication. And solving this recurrence leads to the bound that t of n is at most 2 times the binary logarithm of n, which again, I leave it to you to deduce by simple induction from this inequality. And the conclusion is that asymptotically, our new algorithm now has only logarithmic cost, right? So the factor 2 can be ignored in asymptotically. And also the basis doesn't really matter asymptotically because that only changes a constant factor. So that our new algorithm has logarithmic cost as opposed to our first attempt with linear cost. So this is a better algorithm, and thus our first algorithm was not optimal. According to this paradigm of algorithm engineering, start over if your previous algorithm turns out to not be optimal yet. Now we're doing the same again with our second algorithm, ask whether this is optimal. We may try to find a better algorithm, spend lots of hours in brain power, but what I'm going to do instead, and fail, instead I'm going to prove that this algorithm is indeed optimal under this setting. I'll say more about the setting, namely the setting being that we only count the number of multiplications and that nothing else is permitted, and what is the cost of these multiplications regardless of the argument. And as I keep emphasizing, this is the strength of computer science, with emphasis on science, to prove that something is optimal, to prove that some algorithm is optimal, which superficially seems like we're arguing about anything. We're arguing about any algorithm, even those that have not yet been even considered. But that's really the strength. And making such a statement requires indeed mathematics. Here we get away with very simple and superficial mathematics. Maybe we're going to use the mathematical notion of a degree of a monomial. Okay, so we have designed and analyzed an algorithm that uses at most 2 times log n multiplication, and now we're going to state a lemma with several very simple statements each, but combining these statements yields our claim. So let's look at the first statement. First statement, observe that any algorithm in our sense that starts with input x, which is a monomial of degree 1, right? And if the algorithm uses only multiplication, remember that's our condition here as part of the problem specification, we only allowed to use multiplications, nothing else. Then that algorithm produces among its intermediate results only monomials. No polynomial, no rational fraction, nothing else, just monomials in this one variable x. And that's kind of obvious, right? As I said, it's a simple statement, which you can immediately prove by induction, right? So algorithm using 0 multiplications has only the input itself as intermediate result. An algorithm using 1 multiplication can at most multiply the input x to itself, resulting in x squared, which is a monomial, and so on. So whenever some intermediate results are only monomials, and then we apply a multiplication of 2 such monomials, the result is again a monomial. That's the induction step of this simple statement. Next, equally simple statement says that if the algorithm uses a specific number of multiplications, namely L, then all intermediate results, which we know to be monomials by item A, must have degree at most 2 to the L. So that's kind of like a quantitative strengthening of item A. And why is that true? Again, simple proof by induction. Induction starts, suppose the algorithm uses L equals 0 multiplication, then only its input x is among the possible intermediate results, which is x to the 0, which is x to the 1, and that has degree 1, which is indeed 2 to the 0, the case of induction start L equals 0. And in the induction step, suppose that we have an algorithm that performs L plus 1 multiplications. Then we look at the very last instruction, the L plus first multiplication, and drop that for a moment, resulting in an algorithm that uses only L multiplications. Now, by induction hypothesis, using this L multiplication, all intermediate results will be in monomials of degree at most 2 to the L. And now we look back at the final instruction, the L plus first multiplication, which is going to multiply some, we don't know which ones, but some of these previous intermediate results, which have degree at most 2 to the L by induction hypothesis, and multiplying 2 monomials of degree at most 2 to the L results in a monomial of degree 2 to the L plus 1, which is the claim we want to prove in the induction step. After L plus 1 multiplications, all intermediate results will be monomials of degree at most 2 to the L plus 1. That completes the induction step. Okay, and the combining these two simple statements we just proved means that now let's solve this inequality. Here we have the degree. Here we have the number of multiplications that is used by any algorithm. Right here we're arguing about any algorithm. Here we're arguing about any algorithm. Take the logarithm to base 2 on both sides means the logarithm of n must be at most L, which is the statement. For any algorithm, computing a monomial of degree n requires at least that many multiplications, and that's the statement. So here we have using mathematical concepts like induction, monomials, and degree, we have a formal proof that any algorithm that uses only multiplications must use at least log to the base of 2 log of n multiplications to compute this monomial. And our algorithm, well, it doesn't quite reach that statement, it uses twice as many multiplications, but asymptotically, there's no difference because it's only up to a constant factor. And we have thus proven, indeed, that our second algorithm, the repeated squaring algorithm, is asymptotically optimal. There's no point in looking for asymptotically more efficient algorithm like log n or anything else. That said, now Donald Knuth allows us, and maybe even encourages us, to start optimization, namely optimizing the constant factors. Only now, once we have achieved asymptotic optimality, looking at the question whether in this gap between logarithm of n to base 2, which is the best, the required, and on the other hand, twice the logarithm of n, which our algorithm achieves, whether we can, which of the two cases is the right answer or whether there's something in between. And that's a very involved research question that goes far beyond the current introductory lecture. And if you're interested in it, you can pursue this by yourself. It's a nice problem. But let me emphasize that all these considerations really apply only since we've specified that our algorithms only allow to use multiplication and we're only counting multiplications. If we are also allowed to use exponential function or the logarithm in our algorithm design, then there's an algorithm that also solves the empowering problem using a constant cost, not linear, not logarithmic, but constant, simply by using this well-known equation from basic calculus, right? And you see, it involves one invocation of the natural logarithm, one invocation of the exponential function, and one multiplication, but multiplication of, in general, no real quantities. This is not an integer in most cases, right? So the more superficially more efficient algorithm, it only uses less operations, but that's only superficially more efficient, is achieved by using intuitively extremely powerful operations of exponentiation and logarithm. So this is all to emphasize the importance in our virtues of computer science, which operations are we allowed to use and how much do we charge for each of these operations. Okay, so that was a kind of recap, and now we're ready to move on to a more involved and arguably a real example, namely the example of calculating Fibonacci numbers. You all know Fibonacci numbers. Fibonacci numbers start with 0 and 1, and then inductively the next larger Fibonacci number is defined as the sum of the two previous ones. That's the Fibonacci numbers. And on this and the next slide, we want to investigate and devise several algorithms. We will devise 5 algorithms for computing Fibonacci number, 5 different algorithms with 5 different complexities, decreasing from the first algorithm will have exponential complexity, then one with polynomial complexity, then one with logarithmic, and finally with constant complexity. But all these improvements, well, not all of these, but some of them are achieved by using more powerful operations, more expressive operations that may or may not realistically be supposed to take constant time, which is why it's so important to, in the problem specification, to specify which operations can be used and at what cost. But before looking at the very first algorithm, let us record some simple mathematical properties of a Fibonacci number. And the first property is the observation that Fibonacci numbers grow at least exponentially. Okay, so right, we're going to actually recall the explicit formula for Fibonacci numbers using the algebraic the golden mean, and from that it's easy to write at that. But for now, let us just record that without further proof, and then proceed to our first algorithm, which is simply a recursive algorithm in pseudocode that spells out the mathematical definition as a computer program. And here we go. First, the algorithm deals with the two initial cases, 0 and 1, and then the inductive step case with the two recursive calls. Okay, that's our first algorithm, and the correctness of this algorithm according to the virtue of computer science. Correctness is obvious because it really mirrors the mathematical definition, provided, okay, I need to emphasize that, provided that indeed all these numbers n and particularly the return values are indeed mathematical natural numbers. If we run that algorithm on some actual machine precision, then these numbers might easily exceed the machine length that real machine like 32 bits or maybe even 64 bits can represent. So if you try to implement that, please make sure to use mathematical integers such as long int or big int, or however it's called in your favorite programming language. Anyway, so let's analyze that. And yeah, for the purpose of analysis, let's observe that. Let's simply count the number of additions. Okay, this algorithm uses many instructions, but let's, for simplicity, only count the number of additions and observe that the number of additions satisfy the very same recurrence as the Fibonacci numbers, right? So here is one addition, and yeah, that's simple proof by induction. If this takes at least that fn minus 1 additions, if that recursive total takes at least fn minus 2 additions, then adding this together actually is takes f minus 1 plus f minus 2 plus 1 additions, which is greater, strictly greater than fn. So this is a sketch of the induction step of the proof by induction, that is the number of additions incurred by this algorithm is at least as large as the value, as the Fibonacci number we want to compute. And why to mention that and emphasize that? Because we've just seen that the value of the Fibonacci number grows exponentially. And therefore also we see, which is not at all obvious on first observation, that the number of additions of this algorithm must also be exponential. So as I said, the correctness of this algorithm is obvious, but the computational cost is real high. It's exponential, as we've just seen with this argument proof by induction. Count the number of additions, compare to the value of Fibonacci number, know that the Fibonacci number's values grow exponentially. So then, according to our virtue of computer science, what are we supposed to do with this algorithm? Either prove it optimal. Yeah, it's not optimal. Exponential is really bad. Instead, devise a better algorithm. What is the better algorithm? How can we arrive at a better algorithm? Why is there so much cost spent by this seemingly very elegant, admittedly very elegant algorithm, because so many of the small Fibonacci numbers are computed repeatedly, right? So if you spell out, unroll the recursive calls here, then let's say, for example, the Fibonacci number f2 is calculated when n is equal to 3 here. When n is equal to 4, then the Fibonacci number f2 is calculated here. And here the Fibonacci number f3 is calculated, which in turn involves a call to the Fibonacci number f2. So f2, for example, is calculated twice. And if you really unroll this, you see that particularly the low Fibonacci numbers f2, f3, f4, and so on are recalculated exponentially often, which doesn't seem very reasonable. One way is to kind of store the previous values of the Fibonacci number in some array and use that as a cache. Explicitly write a program that maintains such a cache to prevent a Fibonacci number to be recalculated once it has been calculated. But what I want to do is kind of instead unroll this recurrence in a linear way with a loop instead of recursively. And let's call this the iterative Fibonacci number algorithm as opposed to the recursive one. The iterative Fibonacci algorithm maintains this temporary variable which store the previous two Fibonacci numbers that the algorithm has calculated. So that's also more memory efficient than maintaining an array of all previous Fibonacci numbers. Only the previous two are needed according to this defining equality. And so FibL is short for the last Fibonacci number, and Fib is short for the current Fibonacci number. So in the initial two cases, when n is equal to 0, we are done. And otherwise, this is the previous one when n is at least equal to 1. Then this is the current f1. And this is the previous one, the last one, this is f0. And then here is this loop, while loop, while the index is strictly greater than n, so we want to at least calculate the second, third, and so on. Do something and then decrement n until reaching n equal 1, in which case we're done. So this is a loop that's kind of where the loop index is running downwards as while our Fibonacci number calculations is climbing upwards. So the n is not really used as its value in the index to the Fibonacci number, but only as counter in this loop. And in each loop iteration, we do the following. We calculate the new Fibonacci number using the current and the previous one. And in order to store the current and the previous one before having it overwritten with the new one, we store the previous one here in this temporary variable. We store the current one to be the new previous one, and then we add both. And you can see that and how this is indeed an algorithm according to this definition that linearly climbs up, not recursively, linearly climbs up. Yeah, correctness can again easily be seen by induction, comparing the intermediate values with the defining equality of the Fibonacci numbers. And let's now analyze this algorithm and compare it to the previous one. And the analysis here is also rather simple, namely observes that we only have one loop, and that loop is executed n-1 times, because there's an initial n, and in each iteration n is decremented until it reaches the value 1 when it terminates. So that's linear O of n of executions, iterations of this inner loop. And each execution of the inner loop body involves 3 operations, 2 simple data copies and 1 addition. So the number of additions and assignments that we count here are really linear. It's, 2 times assignments, 1 times addition, and some decrement linear in n. So that's provided that we agreed that we're going to count the number of additions and assignments regardless of the magnitude of the data being added or assigned, right? So recall that I keep emphasizing this virtue of computer science and algorithm design, that we be very clear about which operations are permitted and how much each operation costs. And if in the homework, in the exams, we're always going to either do that explicitly or leave it to you to do so, but it must be done. Because if we choose a different set of operations, then some algorithm may or may not be feasible, be allowed. And also makes a difference if we just count the number of operations or regardless of the data being processed in each operation, or if we take into account the length of the integers processed in, say, an addition. Remember, we had that when we talked about long multiplication. And the same applies here. Namely, if we take into account, or if we want to count the number of bit operations, not just the number of arithmetic operations, but the number of bit operations, where each addition, remember, decomposes into several bit operations, then the cost differs. And to look at that, let's have a look at the binary length of the Fibonacci numbers. Right here we saw that the value of the Fibonacci number grows exponentially, but we had this slide that emphasizes the difference between the value of an integer and the binary length of an integer. The binary length of an integer is roughly the logarithm of the value. So for the Fibonacci numbers, their value grows exponentially, which makes this algorithm prohibitive. But the binary length of the Fibonacci numbers only grows linearly. So that when analyzing this algorithm, not just with the number of additions, but with respect to the number of bit operations, and in particular the bit length of the data, that incurs another factor n. So it's going to be an algorithm with a bit cost n squared, which differs. That's the point. If we count just the number of additions, regardless of the length of the data, or if we count the number of bit operations, which depends on the length of the data, that makes a difference. But this difference in this case is not so large. It's the difference between n and n squared. So it's polynomial in either of the two cases. So if we're just interested in whether polynomial or not, then that's a considerable improvement over this algorithm. That's the observation we just had. Computing the Fibonacci number produces roughly linearly many bits of output. So now with our second algorithm, and in either case, our second algorithm is not exponential anymore, but we have boiled it down to polynomial, linear or quadratic. And so following the paradigm of algorithm engineering, we're back to square one, asking whether this algorithm finally is optimal. And long story short, it's not. Well, we cannot get down. Now it really depends on whether we count additions or bit operations. In terms of bit operations, we cannot get lower than linear. We cannot have less than n bit operations for Fibonacci calculations. Why is that? Well, because simply calculating the last Fibonacci number fn, remember that fn has at least n over 2 bit lengths of output. So any algorithm that outputs fn, simply to output that, must have at least n over 2 bit operations. If we count bit operations, if we choose to only count the number of arithmetic operations, then we can actually do better. And that's the content of the next slide. And here's an excellent, really great question in the chat. And I want to take the opportunity to thank the student for asking that question on behalf of probably many others. And the question asks, how can we know whether we have found the optimal algorithm? How can we know whether we are done, whether we can go home having found the optimal algorithm or start optimizing according to Donald Knuth, or whether we have to try again and look for a better algorithm? And that's so excellent a question that there's an entire field of computer science dedicated to that question, and that field is called complexity theory, and it covers at least half of my concurrent lecture CS422, and goes far beyond that, goes to the P versus NP millennium problem. So that question is so excellent because it has not at all a simple answer. What we do here in Introduction to Algorithms, we present some very simple examples where this question has a rather simple solution, but in general, it's not at all easy. Thank you. Okay, so that being said, we have just completed our first iteration of improving an algorithm from exponential to polynomial and arguably linear number of additions, arithmetic operations. And now we're looking at our third algorithm. And the third algorithm actually uses an additional operation that we have not used so far, namely multiplication of integers. Observe that this algorithm only uses addition. This algorithm also only uses addition, subtraction, and assignment, but no multiplication of integers. And remember, when we talked about long multiplication, we said that it makes a difference if we allow if we count one multiplication as one step, regardless of the size of the data, or whether we count one multiplication in terms of the number of additions, which it can be expressed, or if we count the number of bit operations to express that multiplication. Yes, that again, there's a great question. That difference, that's really the message that I want to convey here with these slides. Two messages. First, whether an algorithm is optimal and how optimal depends on which operations we are allowed to use. And we're just about to devise a third algorithm which uses a new operation of integer multiplication. And it depends on how much cost we charge. And that's really a question of definition, right? Do we define that one multiplication counts as one step? Or do we define that one multiplication counts as n additions? Or do we define that one multiplication counts as so and so many bit operations? And that's right, that's part of this problem specification, which is, I understand, has been so often neglected in many algorithms courses. So that's part of the specification. So when you start to design an algorithm, it's important to specify which operations you are allowed to use: bit operations, arithmetic additions, or multiplication. We'll get to that point after at the end of the Fibonacci section. So please stay tuned, because now we move on to the third algorithm. And this is the algorithm that, yeah, as often in most efficient algorithm, uses mathematical insights. The core to efficient algorithm is mathematical insight, and the insight here is actually very simple. Namely, simply express the definition of the Fibonacci numbers as vectors and matrices. So what you see here is simply the same as this equation, just written as 2 times 2 vectors or matrices, right? So Fn is equal to, let's recall, row times column is equal to Fn minus 1 plus Fn minus 2. That's the definition. And the second row says Fn minus 1 is equal to 1 times Fn minus 1, indeed. So we have expressed that simple equation here as a simple matrix equation in dimension 2. Nothing seems to be gained here, but now recall that we can multiply 2 times 2 matrices repeatedly. So we can now apply the same equation again, unroll it to the, now with n replaced by n minus 1. And we do that again and again. We do that k times. And each time we unroll this, consider this as an inductive equation, we get another power, another factor of this matrix here, right? So if we do that k times, then this is the matrix raised to the kth power. And instead of n minus 1, here it's n minus k. Instead of n minus 2, here's f of fn minus k minus 1. For every possible k, up to n minus 1, right? So when k is n minus 1, then this becomes f0. We cannot go beyond f0. So this holds true for every k, and we're going to apply that to actually where k is equal to n minus 1. Why? Because then indeed here there's f1 and here's f0. These are the quantities we know. These are the quantities that define the Fibonacci numbers. For other cases, these are not known quantities. So it seems like a smart idea to look closely at this case when k is equal to n minus 1, because then this equation gives us an almost explicit expression for the Fibonacci numbers, for the pair, right? Namely, take the vector 0, 1, 1, 0, I should say, 1, 0, right? When k is equal to n minus 1, then this is 1 and this is 0. And multiply it to this matrix, 2 times 2 matrix with these entries. Raise this matrix to n minus 1th power. So this is a mathematical equation, no algorithm, but it suggests an algorithm, which I'm not going to spell out, an algorithm that first raises that matrix to the n minus 1st power, and then multiplies that to this vector. And you all know from linear algebra how to multiply vectors in matrices and how to raise matrices to powers. Well, actually, we remember we talked about algorithms for powering, right? We first had the algorithm that powers by repeated multiplication, which had a linear cost. And then we found this much more efficient algorithm using repeated squaring, whose cost was only logarithmically many multiplications, which means that this expression, raise this matrix to the n minus 1st power, can be calculated by an algorithm that just multiplies 2 times 2 matrices log n times instead of O of n times. Let me say that again. This is an instance of the powering problem. In the powering problem, we considered abstract object x to be multiplied a certain number of times to a certain power. And here, that's the benefit of abstraction. Here we have a specific object x, namely x as a 2 times 2 matrix that we want to be raised to power n minus 1. And our repeated squaring algorithm can do that using only log n minus, well, 2 times log n minus 1 multiplications. That sounds good, right? Logarithm means fast. And it is, except there's a small detail that we are missing, namely the algorithm that we that we take from the previous slide from the powering problem performs log n multiplications of 2 times 2 matrices. But here, we're not allowed to multiply 2 times 2 matrices. Instead, we're only allowed to multiply integers. That's again to illustrate and emphasize the importance of precisely specifying which operations are permitted. In this case, we are allowed to use integer multiplication on top of integer addition, but we're not allowed to do matrix multiplication unless we express the matrix multiplication as several integer multiplications. And fortunately, that's easy to do, right? And you all know how to do that, how to take two times 2 matrices, each with integer entries, and you can express one multiplication of such matrix using 8 multiplications of integers. So expressing this powering uses log n multiplications of matrices, which in turn, each of them can be expressed using 8 multiplications of integers. So the overall cost only increases by a constant factor of 8 when proceeding from matrix multiplication to integer multiplication, because we're only allotted integer multiplication. So that finally we have arrived, and you see how we have arrived at that. We've arrived at an algorithm that really calculates this using asymptotically log n many integer arithmetic, that is log n integer multiplications, and of course integer additions, which we all use all the time anyway. But let us recall how we arrived at this algorithm. And I cannot really spell that out because we've used so many steps of abstraction. First, we've took mathematics to arrive at this equation. Then we have applied the abstract powering algorithm, powering some abstract object, counting only the number of multiplications of that object. And then we had to apply that to the 2 times 2 matrix as abstract object and express the multiplication of 2 times 2 matrix as several, more precisely 8, multiplications of integers, because these we are allowed. And I leave it to you to really boil all this down to an explicit algorithm and maybe even implement it in homework using, for example, the ELI system. But there's a great question in the chat. And yes, indeed, there are twice the same question asked by 2 different people. So congratulations. Again, awesome question. The question is, what about the additions? Professor Martin keeps talking about counting the number of multiplication and doesn't even mention additions anymore. Indeed, yes, we also need to count all the additions. So how many additions does it take to multiply 2 times 2 matrices? Fortunately, that's just another constant. I'm going to say 4, but it doesn't really matter. It's really just a constant number of additions. So the number of additions is going to be roughly the same order of magnitude asymptotically as the number of multiplications up to constant factor. So that's why I've been focusing on the number of multiplications, but indeed, to be fully correct and on the safe side, we should, and with we, I mean you, quod licet Iuvus, you should also redo the same analysis, taking into account also the number of additions. And I mean that. I mean, this is really, really instructive, a great example, a great assignment, a great practice to set up a recurrence for the number of additions and multiplications, solve it and see that in the end, it's going to be what did we say? Asymptotically logarithmic. I am not going to be specific about which factor we're ignoring here in the asymptotic calculus, but it's asymptotically logarithmic number of multiplications and additions. Thank you very much for these two identical and very well justified questions. Okay, so to summarize, this slide now already has our third algorithm for computing Fibonacci numbers using the first two algorithms improved from exponential to linear or polynomial number of additions, and our third algorithm, which is not spelled out, uses logarithmic number of additions and a logarithmic number of multiplications. Multiplications now being used as a new operation and being harnessed, because that's what really seems to allow us to accelerate from linear to logarithmic. If we only count the number of operations of additions and multiplications, regardless of the size of the data being added and multiplied, which depends on our specification. Now, there's another great question in the chat. What if we do not want to just count the number of operations, regardless of the size of the data, but if we want to count the number of bit operations, that is, taking into account the number of operations? Well, then, indeed, we cannot get below linear, because as we observed, already the final result will have a linear number of bits to output, to merely output, so that cannot be beaten. So if we count the number of bit operations, then the second algorithm with quadratic cost, bit cost, is almost optimal, polynomially optimal. And our third algorithm, that's a little bit more involved analysis. Our third algorithm turns out to have bit cost n log n, but I'm not going to perform that analysis here. Right. So there's another question about how to power the matrix. Yes. No, we're not going to diagonalize the matrix. This matrix, this is a Jordan block, right? So it cannot be. Oh no, it's not. Yes, it could be, but that's not what we're going to do. Good question, but that's not what we do. We really power the matrix using the repeated squaring algorithm from 2 slides ago, without diagonalization. Good. Yes, thank you. So that's our third algorithm. And to reiterate each of these algorithms, one can and maybe wants to analyze in different ways, either counting only the number of operations or counting the bit operation, that is taking into account the magnitude of the data being processed. And whether it's that which of the two assumptions is the right one, that's really depends on the application. That's part of the specification, right? That's not a that goes beyond. It's part of the definition, if you like. So that's our third algorithm, but I've promised you 5 algorithms. 5 algorithms you're going to see today. So let's move on to the fourth algorithm. Fourth algorithm, yes, and as I kept emphasizing, the third algorithm makes use of integer multiplication as a new operation. And now we're moving on to the fourth algorithm, which uses the even more explicit formula for your Fibonacci numbers based on the golden ratio. So that leads us to the question, what is an explicit formula? And there's no really good definition for that, because this formula involves matrix powering, and right, and the algorithm we just saw uses logarithmically many multiplications of integer matrix, each one in turn expressed as 8 integer multiplications and 4 additions, so that the overall number of integer multiplications and additions as opposed to matrix multiplications is also only logarithmic in n. And now here we have this famous Binet formula for the explicit formula for the Fibonacci numbers involving the golden ratio. Here you see the formula. If you have never seen the formula, don't worry, takes too long to parse anyway. Not to mention to prove that, it's actually again another nice exercise which I encourage you to do at home. We might throw that in as an exam question, or we may not. You will see. You will see. And that looks also like an explicit, it's commonly considered an explicit expression, but observe that also here we have some powering involved, right? And that's really a matter of taste. Do you consider powering to be explicit, or is that not explicit, like here? Anyway, can we devise an algorithm based on that formula of Binet? Yes, we can. If we are allowed exponentiation, right? And again, this exponentiation can maybe be expressed using our repeated squaring by using log n multiplications of phi, the golden ratio. But observe now we're not talking about addition and multiplications of integers anymore. So we have subtraction. Here we have repeated multiplication. Here we have even division, but not of integers, because the golden ratio is not an integer. It's not even a rational number. It's an algebraic non-rational number. So the algorithm that might be derived or based on Binet's formula is uses even more powerful operations than our third algorithm, because now it uses not integer addition and multiplication, but it uses addition and multiplication of algebraic number, which depending on the specification may be permitted to use or maybe not. In either case, it's a even more powerful operation, maybe not more powerful as on a even larger, more complex type of data, namely algebraic numbers as opposed to integers. And that's our fourth algorithm, which again, I'm not going to spell out, not in pseudocode, not even explicitly, just something based on this formula. And our fifth and final algorithm, and then we're going to be done with this Fibonacci example, is where we even express the exponentiation not as repeated multiplication or repeated squaring of algebraic number, but instead as one single operation or constant number of operations using this formula with exponentiation and natural logarithm. And observe that here we can indeed now express the Fibonacci number using only a constant number of operations, but now these operations are really, really powerful. They involve natural logarithm of algebraic number, which is a transcendental number, and then exponentiation of this transcendental number. And here we have some multiplication of transcendental numbers by an integer. So, so the message to take away here from these 5 algorithms is about the trade-off. The more powerful operation we have, the less of these we may in general need. And if we're only restricted to less powerful operations, maybe even only to bit operations, then the optimal algorithm will incur more and more of these bit operations. That's one side of the trade-off between the number of operations executed by the algorithm and the power of the operations used by the algorithm. One side of the trade-off. The other side of the trade-off is realism. The predictions obtained from our analysis may be realistic, may coincide with your actual runtime measurements when you implement that algorithm. When you implement that algorithm on a computer, at the end of the day, it all boils down to bit operation, because that's what the circuits in your computer do, right? They perform bit operations. They don't operate on transcendental numbers. If you write that in your favorite high-level programming language, then the compiler will translate that into bit operations on your behalf without your having control of it, right? So at the end of the day, when you implement any of these 5 algorithms, the computer will perform bit operations. Now, if you have counted bit operations, if you have analyzed your algorithms in terms of bit operations, then your analysis will coincide, hopefully, probably, with the actual running time, with the actual performance of the computer. If you have in your analysis only counted the number of operations, then the computer will have to boil down these high-level operations into lower level, and may take much more time for that than your superficial analysis may have predicted. For example, your superficial analysis may have predicted constant time, but if you do that on an actual computer, it's going to take much longer than constant time, or even worse, actually, because computers cannot, in general, process transcendental numbers exactly. There will be rounding, so that at the end, the result will be wrong. Yeah, these are the 2 possible cases. Either your runtime analysis will be in mismatch with the actual performance if you only count the number of operations, or your runtime analysis may be correct. The computer uses constant time, but uses approximations, which may in the end give a wrong result, which arguably is even worse. So that's the message I wanted to convey with these 5 algorithms for computing Fibonacci numbers, trading, gradually moving on from elegant algorithm to efficient algorithm, using multiplication, finally using multiplication of integers, using multiplication of algebraic numbers, and finally using the exponential function and natural logarithm on transcendental numbers, which seems to be the most efficient, but also the most unrealistic, either in terms of when comparing with the actual performance or when comparing with the actual value to rounding errors. That's actually, indeed, some of the questions in the chat asked exactly that question. How, what about rounding errors? What about precision issues when talking about square roots, and talking about exponential function, and talking about natural logarithm? Exactly, this is going to indeed happen. So the message is, in this case, the analysis of the algorithm, either correctness or computational cost, will differ from the actual performance of the implementation, and that is exactly the difference. An algorithm on the one hand, and its implementation on the other hand as a program, the virtue of computer science. So yes, that's all I wanted to say about Fibonacci numbers. Very instructive example. Please have a look at it again by yourself at home. And what we're now going to do is we're going to similar devise again several algorithms for polynomial multiplication. But before we get there, these algorithms will be analyzed by devising, this will be recursive algorithms. and we analyze recursive algorithms in terms of recurrences. And then we solve the recurrences, and there's a famous master theorem about the asymptotic growth of recurrences, which we will provide here and then later use when we analyze the algorithms for polynomial multiplication. So here's the master theorem. Let f be a function from natural numbers. You can imagine that to be a sequence indexed with natural numbers to the reals. So the values of that sequence are real numbers, positive real numbers. And let's suppose that the function satisfies the following recurrence relation. So this is looks like one recurrence relation, but it's actually many because it involves all these three parameters, A, B, and D. Okay, so f of n is equal to A times f of n divided by B plus O of n to the D. Okay, and this covers many examples of recurrence relations, and in particular all those that we will encounter when we devise and analyze our algorithms for polynomial multiplication. And let's first discuss how such recurrence relations may arise in the analysis of recursive algorithms. So imagine or recall the divide and conquer paradigm. Divide and conquer paradigm means in order to devise an algorithm for solving a big problem of size n, let's try to decompose that problem into A subproblems, each problem being B times smaller than the original. Okay. So let me say that again. Let's suppose you have a problem of size n, and if you're lucky, you can maybe decompose that into three problems of size n over 3. That would be very good, because then there's basically no overlap. What would be a little bit worse is if you can subdivide this into 3 problems, but each one is only size n over 2, which means there is some overlap. And there are many more possible combinations of decomposing the problem following the divide and conquer paradigm, which we'll talk about in much more detail in the last chapter 7, but just to give you some motivation for why we consider this recurrence relation. Then the decomposition phase, the first phase, also may take some time. Let's say it takes time O of n to the d, for example, quadratic time or cubic time for the decomposition phase. And then come the recursive calls to the A subproblems of smaller size, how much smaller indicated by B. And at the end of the divide and conquer phase, there comes the recombination part where our algorithm may produce the final output by recombining the results of the several of the A recursive calls, which again may incur additional cost, which we also supposed to be covered by this. So this includes this term in our example later. We'll cover both the decomposition phase and the recovery phase, and this is the recursive call phase. This is why this simple recurrence covers so many examples of analyzing recursive algorithms. Now, what is the asymptotic growth of the solution to this recurrence? Well, it's hard to really find an explicit expression, but asymptotically, that turns out to be fairly simple, because one of the benefits of asymptotics is that we can ignore and drop constant factors, right? So here in this example, A and B and D are supposed to be natural numbers and constants in particular, and only n grows. So in the solution, A and B and D will occur as constant, but will often be omitted because they are constants. Right. And asymptotically solving this occurrence then in turn gives also solves our analysis of the computational cost of the algorithm that we're going to devise about for polynomial multiplication in this chapter. And here's the answer to the asymptotic growth. And it's actually, there are three cases. Well, we would kind of expect that depending on the value of the parameters. So the first case is if A is strictly less than B to the D, this D, then the asymptotic growth of a solution is like N to the D. And the actual value of A and B does not matter. That's somewhere here hidden in the big O calculus. If A is strictly greater than B to the D, then the solution grows asymptotically like this. Notice that these two cases are polynomial growth. All three cases are polynomial growth, but the exponent is different. Here's the exponent is D and does not depend on A and B. Here the exponent is the logarithm of A to base B and does not depend on D. And then there's this intermediate case where between strictly less and strictly greater, there's actual equality. And in this case, there's an additional factor of log n, which is kind of spurious or anyway. So this is the master theorem. We won't prove that. That's a subject of discrete mathematics. We will use that when we design and more precisely when we analyze algorithms for the polynomial multiplication problem. So here's a quiz, and maybe we'll end with that quiz. So we have, not last time, but just now devised and analyzed 5 different algorithms for computing Fibonacci number. Recursive one, an iterative one based on matrix powering, one based on Binet's formula with repeated squaring of algebraic numbers. And what I've omitted here is the 5th algorithm that actually uses a natural logarithm and exponentiation of transcendental numbers. And I recommend for you to, for each of these algorithms, state which primitive operations it involved, over which domain, and what asymptotic computational cost each of these algorithms incurs, in what measure of computational cost, and which of the algorithms has the lowest bit cost if you boil down everything to bit cost. So this is a quiz for today. Please think about it and type your answer in the chat.